In this video, we will talk about the law of conservation of linear momentum. We shall start with the definition of a linear momentum, and we will see how it relates to Newton's second law of motion, which will bring us to the law of conservation of linear momentum, and we will finally do some solved problems based on the concepts discussed. Now, the symbol we use to denote the linear momentum of a particular object is little p. As you can see, there is an arrow there that signifies that momentum is a vector. Now, it is a vector that is associated with the state of motion of that particular object. More specifically, the mathematical definition of linear momentum is as follows. The linear momentum equals the mass of the object times the velocity of the object. So since there is this velocity here, that is what we mean by the statement that it is associated with the state of motion of an object. Now the SI unit for this linear momentum, as you can see, is, since mass is quantified in the unit of kg and velocity is quantified in the unit of meter per second, so the SI unit for linear momentum is quite simply kg meter per second. Another thing to note is the direction of this linear momentum is parallel to the direction of the velocity of the object. So if the object is moving to the right, its velocity is to the right, its linear momentum is also to the right. That is exactly what this equation is saying, because mass is a scalar. To give you an idea about what we have just discussed, look at this particular mass. The mass of this object is 2 kilograms. Now let's say it's moving to the right with some velocity, denoted 3 hat meter per second. Now we have taken, of course, the x-axis, the positive x-axis, to be in a rightward direction. So this I hat signifies the unit vector along the positive x-axis. So since the direction of the velocity is I hat, what would be the momentum, the linear momentum of this object? It is quite simply the mass 2 times the velocity, which is 3 hat, and you get 6 hat kg meter per second. Now as you can see, the direction of this momentum is also I hat, just like its velocity. So this vector and the velocity vector are parallel to each other. Let's look at this particular example. So this is a two-dimensional example. So you have, again, an object with mass 3 kilograms moving in an xy plane with a velocity of 4 I hat minus 3 j hat meter per second. So xy plane means that. So what is the linear momentum for this object? Well, it is the mass, again, 3 kg, times the velocity. The velocity is 4 I hat minus 3 j hat, and that's going to give you 12 I hat minus 9 j hat kg meter per second. So in vectoral language, this is just a scalar multiplication of the velocity vector with the scalar mass, 3 kg, giving you the final result, 12 I hat minus 9 j hat. So this 12 here is the x component of this linear momentum, and minus 9 is the y component of this linear momentum. Note that in this diagram, which essentially it is a one-body system because there is only one mass, we have chosen to give the velocity slightly in terms of angle, slightly differently. So the speed is 2 meters per second at an angle of 30 degrees above the horizontal. So of course the magnitude of the momentum is simply 4 times 2, which is 8 kg meter per second. Now the x component of this momentum, the linear momentum, is that arrow right there, px, and the y component is that arrow right there. So px is 8 cosine 30 degrees, and Py is 8 sine 30 degrees. Both are in the unit of kg meter per second. So that means the complete description of the momentum vector, the linear momentum vector, is 8 cosine 30 degrees I hat plus 8 sine 30 degrees j hat, which is just 6.93 I hat plus 4 j hat kg meter per second. So this is a system with two bodies, 1 kg body and 2 kg body. So if you want to calculate the momentum of this system, the linear momentum of the system, you simply have to add up the momentum of the first object and the momentum of the second object. The momentum of the first object is simple, is the mass is 1, the velocity is 3 I hat, and that's it. The mass of the second object, the 2 kg object, would be 2 times. The velocity has two components. One is the y component, and the other one is the x component. X component here is negative. So the x component will be minus 2 cosine 10 degrees I hat, and the y component is 2 sine 10 degrees j hat. So which is just by adding this to this, you get minus 0.94 I hat plus 2 times 2 sine 10 is 0.69 j hat. And that is the momentum of the system, of the two-body system. Next, let's see how linear momentum is connected or related to Newton's second law of motion. Now we know from our previous videos that Newton's second law is given by that net force equals mass times acceleration of an object. So if you have an object and it's subjected by a net force, F net, then we know this object with mass m will accelerate with acceleration a. Now we also know that acceleration is given by the time derivative of velocity vector. So if you put this information in here, you will get m times dv dt. Now m is a scalar, so you can absorb that under the derivative sign, and that will simply give you d dt mv, which is d dt. mv is just linear momentum, and that's exactly what you get. So the net force acting on a particle equals the rate of change of linear momentum of that particle. So that is another way of looking at Newton's second law of motion in terms of linear momentum. That brings us next to the law of conservation of linear momentum. So now let's assume you have a system, but the system is isolated or closed. So that means there is no net external force acting on the system. Now, from the previous equation that we wrote down, namely, if there is no net force on a system, since net force is related to the rate of change of momentum, so if there is no net force on the system, that means the rate of change of that linear momentum of the system must also be zero. So when we say the momentum, the linear momentum of the system does not change with time, we are simply saying that the initial linear momentum of the system is the same as the final linear momentum of the system. Initial and the final states referring to two different states in time. Let's apply the concept to the following problem. So what do you have here? You have a man holds a rifle with mass 3 kg, and this rifle fires a bullet of mass 5 gram horizontally with a velocity of 300 meters per second. Now calculate the recoil velocity of the rifle. Now of course we have to assume that the rifle bullet system is an isolated system so that the conservation of linear momentum holds. So this is a two-body system. Let's look at the initial state and the final state. So this is the rifle, and you have bullet inside. So the initial linear momentum of the system consists of the initial linear momentum of the rifle plus the initial linear momentum of the bullet. And none of them are moving, so they are just zero. So the initial linear momentum of the system, of the rifle bullet system, is zero. Now what happened after, or the final state? The final state, what happens is that the bullet is shot and it is moving to the right, let's say with to the right with a speed of 300 meters per second. And of course we know the mass of the bullet is 5 grams and the mass of the rifle is 3 kg. So now we have to write down the final linear momentum of the system. So the final linear momentum of the system consists of the final linear momentum of the rifle plus the final linear momentum of the bullet. Now what is the first term? The final linear momentum of the rifle. It's 3 times some recoil velocity of the rifle. Let's assume the recoil speed is Vr, and of course it's going to recoil, it's going to move towards the leftward direction. And the momentum, the final momentum of the bullet is 5 grams, so you convert that into kilograms, times the velocity is 300 I hat. I hat because the bullet is moving to the right. Now when you equate the momentum before and momentum after, you can solve for the only unknown, which is the velocity of the rifle. And that will give you Vr as minus 0.5 meter per second in a direction of minus I hat. So the rifle will recoil backward or leftward with a speed of 0.5 meter per second. And that solves the problem. Let's look at another problem. Assume you are standing on ice, so there is no friction between your feet and the surface of the ice. Your friend throws a 0.5 kg ball at 10 meters per second in your direction. So forward towards you. Now, if your mass is 70 kilograms and you catch the ball, with what speed you and the ball will move afterward? So the situation is depicted in this diagram below. This is before you catch the ball, and this is after you caught the ball. So again, this is a two-body system, ball and yourself. So the initial linear momentum of the system is the momentum, the initial momentum of that ball, plus the initial momentum of you, the person. So the ball is moving rightward. The mass is 0.5 kg, and the velocity is 10 I hat because it's moving to the right. You are stationary, you're not moving, so your momentum is 0. So that means the initial linear momentum of the system is 5 I hat. Of course, the unit is kg meter per second. The final linear momentum of the system equals the mass of the person, your mass, plus the mass of the ball, because now both masses are moving as one, times the common velocity of you and the ball. So it is 70.5 the final velocity of you and the ball moving to the right. Now we know that this surface is frictionless, which means there is no net external force. So that means the momentum is conserved, and you can equate the momentum before to after. So that means 5I hat equals 70.5 Vf, and you can solve for the speed with which you and the ball will move afterward, which will be 0.0709 I hat meter per second. So the velocity is 0.0709 I hat meter per second, or the speed is 0.0709 meter per second. And that solves the problem. Thanks for watching.